on the topic of information interactions in outcome prediction, quantification, and interpretation using stochastic block models.
Okay, thank you for the introduction. Hello everyone, my name is Poux-Médard. I'm a PhD student at the Université de Lyon, France, under the supervision of Julien Velsin and Sabine Luce. And I will present you our work on information interactions in outcome prediction, a study using stochastic block modeling. So, first of all, let's understand the title. By information, we mean when the effect of several parts is more than their sum. So that's why I try to illustrate here on the pictures. So if for some reason red implies green and blue implies green, it doesn't mean that red plus blue implies green either. So we said there is an interaction. So interaction between what? The parts that interact, we refer to them as pieces of information. They can be tweets, they can be posts, they can be words, etc. There are pieces of information that are likely to give an outcome. So for tweets, for instance, the outcome can be whether the user will retweet or not. For a post, it can be a like. For words in a message, it can be an answer to that message, etc. So concretely, resolution, I'm sorry. What we're trying to do, our task at hand, is to predict, for instance, on Spotify, on a user-generated playlist, what is the next song a user will add to the playlist given the interaction between a list of previous songs that have already been added to a playlist. We also have a Reddit data set where we'll try to predict the named entities in an answer given named entity in a given message. On Twitter, we'll try to predict whether a tweet will get retweeted or not, given the history of exposures of the user to other tweets. And finally, we have a symptom diseases corpus where we're trying to diagnose a disease given the interaction between pairs of symptoms. So a bit of background first. There is a seminal work on interactions that are tackling the same problem as us. It's Myers 2014. So in this work, the authors are trying to model interaction as a small modification of a base virality, so which is fine. However, there's a problem in this article. They assume that the base virality is equal to the frequency of an output in the data sets. But the problem here, what I illustrated is, for instance, imagine all of the interactions are positive terms. Then when you compute the frequency of an output, you're already taking into account the interaction terms when you do that. So if the base virality is in red here, the frequency is in green. If all of the interactions are positive, we're already above this quantity that you use to define interaction. So there is a problem. So the point of this slide is to explain why virality or base probability of an outcome has to be inferred along with the interaction terms in order to be valid. So to do so, we use a well-known model, the mixed membership stochastic block model, and we make a modified version of it. So since we're considering an ordered set of entities in our prediction, we want our model to be permutation invariant since the order doesn't matter. So concretely, we want the probability of X given a pair A and B to be the same as the probability of X given a pair B and A. So we develop an EM algorithm, expectation maximization algorithm, on previous work, especially Good-Euler-Ritz 2016. So our motivations, we have applied motivations, so those are the questions we want to answer. Can we use interactions in order to optimize recommendations? Yes, we can, so I will show you the numbers later. Does interaction modeling help recover semantic links, between entities? Yes, it does. How frequent are significant interactions? We will show later that they are rare. And does interaction usually lead to large or small modification? Most of the interactions are small, so they modify very slightly the probability of an outcome, as I will show you later. So our model, first of all, the data we consider. So here I'm just recalling the structure I already gave before. We have a structure message answer. In a message, we'll consider all of the pairs. Here, for instance, the pair will be AA, AB, AC, BB, BC, and CC. And we'll link each of those pairs to every of the entities in the answer to that message, to that signal. This is that I would consider. And note that we allow for self pairs like AA, BB, and CC. And those will account for virality. So that's how we'll infer the base probability of an outcome given only a single information with an interaction. Our model reads like that mathematically. So there are two quantities that we aim to infer, a membership matrix, where for each piece of information we'll try to associate to what cluster it belongs and to what extent. So a vector, an entry of theta e is normalized to 1. And the interaction matrix pKL of x is the probability of an outcome x given cluster K on L. So what is this equation exactly? It's simply a linear combination. So to what extent each of the pieces of information belong to each clusters. Then we make the cluster interact. It's like a weighted average of the interaction given the membership vectors of each entity. And so now let's switch to the experiment. So I'm just reminding you what data we're considering. So we're trying to predict next song in Spotify given the songs that have already been added by a user, words in an answer to a message, whether a tweet will be retweeted or not given a history of exposures to tweets, and a disease given a list of symptoms. So I'm not spending much time on this slide. So those are the numerical results. So we test our method against 3 proposed baseline on the 4 data sets, and we present here 3 metrics. About the experimental setup, we perform a 5-fold cross-validation, we do 100 run, I think, per fold for each data set. And so, except for the Reddit data set, we seem to consistently outperform the proposed baseline, which are the naive one, the MMSBM, which is the same model as ours, but without the interaction terms, and an upper limit that we derive that comes from our evaluation process. So we computed that on the test set. It is a maximum performance, even a perfect model, given the way we evaluate our model, cannot go beyond this limit. So another nice feature of the model, it makes well-calibrated predictions. So quickly, marginal calibration is when the frequency of an output in the test set is equal to the assigned probability of that output in the test set. So the closer to 0, the better. Here I computed the difference between the frequency and probability of an outcome, and we see they are quite close to 0. So this is a nice result too. And finally, I told you that base virality must be inferred at the beginning of the talk. So here I'm plotting the base virality as it has been defined before as the frequency of an outcome in the test set, in the training set, versus the virality that we inferred using the IMM-SBM, our model. And we see that there is typically a 10 to the power minus 2 difference between the two quantities. So it makes it hard to spot interaction of the order of 10 minus 5 on the probability when you might start with a 10 minus 2 error. So that's another argument of why virality must be inferred. And finally, about the findings. So they correlate with previous works done on interaction modeling. Here on the x-axis, we plot the relative variation in the outcome probability that's due to the interaction. So minus 100%, it means that the probability has been completely cancelled. 100%, it means it has been doubled. We see that most of the interactions are small, so they are close to 0% in change on the probability, but a significant number of them are leading to huge changes in the probability of an outcome. So that correlates with the finding of Myers 2014. And here we propose a visualization. So this is basically the matrix I told you about, the cluster interaction matrix, pKL. So each of the line, each of the column is a cluster, and the color code represents the average, the overall impact of the interaction between those two clusters in the probability of an outcome. So it is. So what we can see on this picture is that significant interactions take place between very specific clusters, and that for most of the clusters, interactions have very small magnitude, but still present everywhere. So that's why it's yellowish and not whitish. So those are our findings. So as a conclusion, I'm just recalling what I just said. So we developed a state-of-the-art model, the MMSBM, into its symmetric version, the IMM-SBM. We applied it to burden and correct previous conclusions on interaction modeling with a clean definition and inference of virality. We find that interactions are weak and sparse, and we sketch leads for applications in recommender systems. Like, for instance, this can be used to know where to put a Twitter post in the history of a user to maximize its likeliness of being retweeted or liked or whatever. It can be used in playlist building, how to suggest the right video to a YouTube user that's going in automatic mode, or suggest short answers on, as it's already being done on Gmail, for instance, given a text like a thank you, or you find attached the piece. Here is. Thanks for your attention.
Thank you, guys, for this great talk. I would maybe have a question. So regarding stochastic block models,
Yep.
they usually you need to predefine clusters as an input. So in such a model, and at which point do you calculate the clusters, and can you also work with predefined clusters?
It works pretty, what I have to define in the first place is the number of clusters that I will use in my embedding, if that's your question.
Yeah.
Yeah, I've got a slide for that. So here it is. That's how I did. So basically I ran experiments for a large number of clusters. And here the green line is the cluster I chose. So I chose it according to the elbow method, which is when the performance stops increasing, stopping here, and I'm using this number of cluster.
Yeah, thank you.
Welcome.
Also, since such a model is, in a sense, close to a matrix factorization model, would you say that it could be used in in recommendation use cases where factorization models are applied?
Yeah, sure. Well, in the reference I showed Godoy-Lurie to 2016. In this paper, they also show that the MMSBM is a generalization of the matrix factorization model. So yes, of course, it's matrix factorization model. It's when you define some parameters in a precise way in the frame of the MMSBM model. So yes, we can just transpose it to the applications indeed.
Okay, thank you. And also one other question is so that since it's also applicable in session-based recommendation systems, would you also considered, or have you also considered comparing it to state-of-the-art session-based recommenders? Or so this is more of an application of the model?
This is more like an application,
yeah.
Because, yeah, I didn't, well, to be honest, the original model, the MMSBM, hasn't changed that much. I tweaked it so that it can consider an order set as an entry, so I enforce some symmetry in the modeling, but the main focus here is how to evaluate the interaction, compare that with the previous works that have been done on the topic. So it's not that much of a technical work, that's why I evaluate only with the original baseline, a naive one, and I'm not doing a complete state-of-the-art with 20 other models tackling similar problems.
Yeah, got it. All right. Thank you very much.
Thank you.
And with this, I think we can conclude the session. I would encourage everyone, if there are any more questions, just to approach the presenters at the coffee break or online in the questions and answers. Thank you very much. We also have an online virtual sponsor meetup. Thank you.